Okay, talking about systematic and random error. These are things when we're considering how accurate our results are, how precise they are, and what's influencing those things. The different types of errors that might be influencing our results, and which ones affect accuracy and which ones affect precision. So accuracy and precision are two terms that we often mix up and misuse. I see it all the time in lab reports and people using them in class. I probably do them myself, but it's very important that we can tell the two apart. So accuracy is how close the value is to the true or accepted or the literature value. Those are all different terms we use for the true value. Whereas precision is how close together a series of measurements or calculated values are. You can also think of it as how repeatable a series of measurements are. So a simple example that often gets used is like a dartboard. Accuracy would be being close to the bullseye. And precision would be having all of the shots or all the darts ending up close together. So the ones on the right represent precise shots because all the shots end up in the same spot. However, the one here on the top right is inaccurate, whereas the bottom one is both precise and accurate. In this case, the shots aren't very close together, but when you average them out, they sort of all average out in the correct area. So they're relatively accurate, but not very precise. And this one is neither accurate nor precise. When we determine our accuracy and precision, precision is more or less going to be determined by how precise our equipment is. What's the smallest increment on our equipment? For example, this balance on the left that reads to the tenths of a gram versus this one that reads to the tenths, hundredths, thousandths, 10,000th of a gram. Well, this one on the right is much more precise. Let me just fix my font here. So essentially, more decimal places on a piece of equipment means it's more precise. Because if you take a bunch of readings, the range on those readings is going to be much closer together than it would be on this one. Where on this one, after the tenths place, maybe multiple readings you can keep the tenths place in common, but you wouldn't know anything past the tenths place. So your samples could be different when it comes to the hundredths of a gram. Whereas in this one, you can be sure that they're consistent at the tenths, at the hundredths, and even at the thousandths of a gram. And then maybe there's a little variation at the 10,000ths of a gram. Okay. Accuracy, the only way to really know if you're accurate is, again, like I said before, comparison to a standard. Hopefully by now you've listened to the Radiolab podcast about Le Grand K, which is the kilogram. It is the standard for the kilogram. So the only way you really know if you're accurate is by comparing back to that. So 4 different balances here. The top two would represent, if this gray thing is the Grand K, then this balance is accurate, but not that precise. This balance is accurate because it's right at a kilogram, and it's super precise out to 4 decimal places. This one on the bottom is not accurate because it's off by 20 grams. It's also not very precise. This one is not very accurate because it's off by 20 grams, but it is much more precise than that balance. Okay, systematic errors. Systematic errors are errors that cause inaccuracy, that affect our accuracy, okay? And systematic errors always affect results in the same direction. That's sort of your IB definition of what a systematic error is. If you have a systematic error in your lab, it's always going to make your readings or your values too high, or it's always going to make your values too low. It doesn't vary back and forth. And where do they come from? Well, we've already seen they can come from your equipment if it's not properly calibrated. So maybe the thermometer just always measures too high. Maybe the balance isn't set up right, and so it always measures the mass too low. That's examples for equipment. It can also come from how you're doing your method or your own technique. So you might forget to balance or zero a balance. You might read a meniscus from above or from below, which throws off the volume reading. Reaction time. You might always be late on measuring how long it takes for a reaction to happen because of your reaction time. You might have a lack of insulation in some sort of an experiment. One I didn't add before, so lack of insulation. So if you're trying to measure like an energy value or a change in temperature, if there's insulation, you're losing heat, that's always going to impact your results in one direction. When you assess accuracy, you pretty much have to assess it at the end of an experiment. You can do it quantitatively by looking at the error or the percentage error of your final value. So error is just how far away you are from the true value. So simple subtraction, the literature value minus the experimental value. And so you could be, 1 gram off, 2 grams off. You're just finding the difference. Percentage error is a little bit more useful. You take that difference, that error on top, and you divide it by the literature value. So it's a way of looking at how big a deal is your error? What percentage error do you have? Because if you're 2 grams off, but your literature value, is 1,000 grams, then that's a pretty small deal. That's not a big deal to be only 2 grams off for 1,000. But if the value you're going for is 4 grams and you're 2 grams off, then that's 50% error, and that is a big deal. So percentage error can give a little bit more context to how big the error is. So they're usually not realized until the end, these systematic errors. And a big focus of a lab report's evaluation section in IB is going to be trying to figure out what the most likely sources of systematic error are and how could they be realistically improved. Just a special note, occasionally systematic errors cancel themselves out when you're processing. So if you have a thermometer that always reads 5 degrees too high, but then you calculate a change in temp, when you actually do the subtraction, those values might cancel themselves out. So let's say your change was from 50 to 70. So final temperature 70, initial temperature 50. That means the change equals 20 degrees. Well, if your thermometer measures 5 degrees too high, you'd get 75 and 55, and so the change would still equal 20. So sometimes if you subtract 2 values or add 2 values, well, usually if you subtract 2 values, it's possible for the errors to cancel out. Not something to rely on, just wanted to point it out. So precision is affected by random errors. Random errors, IB way to think about them, are errors that can affect results in either direction, making them too high or too low. There's lots of different sources that could lead to this. Most commonly, we're going to worry about our equipment, the precision of our equipment. So the smallest increment on our equipment limits how certain we are about our measurements. With the example of the balances, whether or not I know a reading to the tenths of a gram or the hundredths of a gram or beyond, that determines how certain I am about my measurement. And we quantify this we call this the uncertainty of our readings. So uncertainty, what I highlighted in red, is pretty much going to be your main source of random error that you guys have to worry about. And it comes from any time you take a measurement, there is some uncertainty in that reading, and that's a source of random error. Sometimes we have digital equipment and it's really sensitive, and so the values on it actually go up and down, they fluctuate. And so at that point, you kind of have to take your best estimate of what's sort of the average value on that equipment. And so clearly there's some uncertainty in what the exact value is if your machine is fluctuating. Other things like human limitation, reaction time deciding on exact color changes can put a little bit of variation into results. That can be harder to quantify. But just being able to recognize that we have our own limitations that could make us interpret things either on the low end or the high end. Environmental conditions, random things happening. If you're doing a lab and someone opens the door and there's some wind or it changes the temperature, that could influence results in a particular way. We try to prevent these, and that we try to design them out of our procedures, but obviously things can happen. And then there's things about what you're testing that could have variation that you're not aware of. Down the road, if you decide to do an IA on something biological like oranges or apples, there's going to be a lot of random variation based on how those fruits were grown and how they've been stored. But it could also be that way for solutions or substances in the lab. If they're really old, maybe they're not as pure anymore. Maybe they've mixed with water as they've been stored on the shelf. So there could be variation in our substances just depending on their age and things like that. So assessing precision, you can sort of know as you're going along how precise your equipment is, and by recording uncertainties, you get a pretty good sense of how precise you are. And to assess precision on our final values, we have to take those little uncertainties on measurement and figure out a way to propagate them through to the final values. So we try to limit those random errors as best we can, but we're not going to be able to ever get rid of some of the uncertainty in our measurements. There's always going to be some, and so the best we can do is process it and report it with our final values. Right? So these are the rules for recording uncertainties. I'm just going to call these other instruments. Okay, so I'll go through them quickly, and we can rediscuss them in class. But you are expected to know these rules, and you can print these out and keep them in your notebook and refer back to them. But essentially, if you are using a digital instrument, so that's like a digital balance or a temperature probe or any of the Pasco probes, the uncertainty from that instrument is plus or minus 1 of the smallest increment. So on the balance, if the balance reads to here, then the uncertainty would be reported as plus or minus 0.1 grams. So whatever the last digit is, you'd say that the value is plus or minus 0.1. So what does that really mean? That means if the reading on the balance is 2.4 grams, you would say it's 2.4 grams plus or minus 0.1 grams. And so what that really means is that all you know about that measurement is that it's between 2.3 and 2.5 grams. So plus or minus means that you really know the value within this range. Okay. So any digital instrument, it's plus or minus 1 of the smallest increment. With other equipment, other instruments, the uncertainty is half of the smallest increment of that piece of equipment. So this is like if you're using a graduated cylinder, one of those alcohol thermometers where you can see all the lines on the piece of equipment, then you estimate the uncertainty as half the smallest increment. So what I mean by that, if you have the smallest increment is 1 cm cubed, then the uncertainty would equal 0.5 plus or minus 0.5 cm cubed. Same thing goes for temperature reading, but let's say if you had a volume reading then on this type of graduated cylinder, you know it's 21, the smallest increment is 1, so you're still going to estimate this last digit. So 21.3 plus or minus 0.5 cm cubed. Okay, be good about our superscripts. The smallest increment, you have to assess that with any piece of equipment, and then the uncertainty should be half of that. If you have one of those digital things, digital instruments, and it's fluctuating, you have to just do your best, look at the range of values that it's fluctuating between, and then you can report the value as right in the middle of that range, and you can make the uncertainty half of the fluctuation. So let's say you're watching a device, we'll call it a balance, and it's fluctuating between 2.0001 grams and 2.0009 grams. Well, you could call your measurement that, and you could say plus or minus 0. Okay. So if you see the fluctuation, right, you kind of pick the center of that range as best as you can estimate, and then you report the uncertainty to cover all those values that you saw. So by saying plus or minus 0.004, it covers these other values. Once you've recorded your uncertainty, you have to check a couple things. First of all, you should only ever have 1 digit of uncertainty. The reason why you only want 1 digit, if I'm uncertain about something, like if I know that I have that 2.4 grams plus or minus 0.1 grams, so I know it's between 2.3 and 2.4. If I'm uncertain about this value here, and all I really know is that it's between 2.3 and 2.5 grams, then I have no business telling you that it's well, if it's 2.4 grams, it would be kind of silly if I said it's 0.10 or it's 0.15 grams plus or minus. Because if I'm uncertain about the 10th place, then I'm like ridiculously uncertain about the 100th place. So why should I even write that? So in my view, you never give more than one digit of uncertainty because you don't know anything about it. So you can only really be uncertain about one digit, and then obviously you're uncertain about anything after that. So only give one digit of uncertainty. The other rule is that with your measurement, if I only have this, if this digit is uncertain, this tens place, then my measurement needs to be written to that same exact decimal place. For example, if I use the same example again, so if I write down that my mass is 2.456 grams and my uncertainty is plus or minus 0.1 gram, well, what I'm saying with this uncertainty here is that I'm uncertain in the tens place, right? So if I'm uncertain in the tens place, then I have no business reporting anything beyond the tens place because I barely know about the 4. I know it's pretty close to 4, but I don't know anything about these two digits, so I need to get rid of them, okay? And so in that case, you always need to round off your measurements so that they match your uncertainty. So then we'd round this to 2.4, or if we followed our rounding rules with the numbers I used, it'd become 2.5 plus or minus that 0.1 grams. So you should always have the same number of decimal places in your number as in your uncertainty. Okay. All right, last thing, calculating with uncertainties. When you add or subtract numbers with uncertainty, you need to add the uncertainties together. So if I have 2.4 grams plus or minus 0.1 grams plus 2.4 grams plus or minus 0.1 grams, well, it equals 4.8 grams plus or minus 0.2 grams, okay? Well, the reason being, 2.4 grams plus or minus 0.1 grams, all I really know is that it's 2.3 to 2.5, right? And I know the same thing about the next value, 2.3 to 2.5 grams. So if I think about the extremes that are possible when I add these things together, the lowest end would be like 4.6 grams if it was 2.3 and 2.3. If that's really what the values were, I don't know. They could be 2.3, right? I'm uncertain about it. So 2.3 plus 2.3 would give me 4.6. If it was actually the highest values, then I'd end up with 5.0. Okay? And so if I then turn that into a range, I pick right in the middle, 4.8 grams plus or minus 0.2 grams, and it actually works out perfectly. This right here means the same thing as from 4.6 to 5.0, right? So the uncertainty is telling me the full range of values that it could be based on how well I know these readings. So when we add or subtract numbers, you can just add up the uncertainties that you recorded. Okay, with multiplying and dividing, it gets a little bit trickier, and I'll try to show you an example of why that is. So let's say you're trying to calculate something like area. It'd be pretty weird to calculate area in chemistry class, but I suppose there's a possibility. Anyways, area is the length times the width of a square or rectangle. So if your length and your width were both 2.0 centimeters plus or minus 0.1 centimeters, when you multiply them, it becomes 4. 2 times 2 is 4. But the units change. When you multiply units together, they get multiplied as well. And so now the unit is the centimeter squared. So now we can't just add our uncertainties when we're multiplying or when we're dividing. Because as you can see, if I just add the uncertainties, now the uncertainty has a different unit than the actual calculated value. And that's an issue because having 4 centimeters squared plus or minus 0.2 centimeters doesn't really mean anything. So end of the story is that we can't really, this doesn't work. We can't just add them together when we are multiplying and dividing. So actually it gets a bit more complicated. And there's like a 3-step plan on how you deal with calculating uncertainties when you're multiplying or dividing. So A different way to represent uncertainties is as percentages. So if we look at that example again that I did before, if I take those 0.1s that are uncertain, and instead of representing them as 0.1 centimeters, I turn them into a percent. Well, how do I turn them into a percent? 0.1 cm out of 2. So what is 0.1 out of 2? And I can times it by 100 to make it truly into a percentage. So having an uncertainty of 0.1 centimeters on a 2 centimeter measurement is actually the same as having 5% uncertainty. 5% of the 2 centimeters is uncertain. So you could actually rewrite your calculation like that, where instead of having it with a unit, now it says I've got 2 centimeters plus or minus 5%, and I've got 2 centimeters plus or minus 5%. Well, the cool thing about percentages is that they don't really have units. So that means that when I do the calculation, I actually can add them together. I can say it's 4 centimeters squared plus or minus 10%, right? So if I turn them into percentages, that allows me to add them together. So that's actually what we've just done is step 2. So the first step is this, turning your uncertainties from what we call the absolute uncertainty, where it has a unit, into a percentage uncertainty. That's step 1. Step 2 is you add together all the percentage uncertainties. So now I've got, it should say plus or minus. I've got plus or minus 10%. That's my total percentage uncertainty. And then the last thing that you do is you take this value, the final value, with the percentage uncertainty, and now we want to turn it back into an absolute uncertainty, something that has the unit. So then the question here is, what's 10% of 4? Well, turn 10% into a decimal, so that's 0.10 times 4. It's 4 centimeters squared, and there's a reason we want to put the unit back in now. So what's 0.1 times 4? Well, that's 0.4, and now it's cm squared, and this is our plus or minus again. So now I've got a final answer of 4 plus or minus 0.4 cm squared. So as a recap, here's our final answer. Recap was, when we are dealing with multiplying and dividing with uncertainties, it's a bit of extra work. We've got to take our uncertainties. We can't just add them together anymore. We have to first turn them into percentages to get rid of the unit. So divide the uncertainty by the measurement, you get it as a percent. Then you can add up those individual percent uncertainties to get the total percent uncertainty. And finally, you can take that percentage, turn it into a decimal, and turn it back into an absolute uncertainty for your final value. Okay? It's a lot of extra work, but it's what we have to do if we want to be able to represent final values with accurate, honest amounts of uncertainty. Okay? So then what does this mean? What does this value really translate to? It means that we know the area is between 3.6 and 4.4 centimeters squared. And that's what that uncertainty range means. Other calculations, when we average things, it should actually reduce our uncertainty. It should reduce the range. So you get to kind of do a special thing, sort of like if you had a fluctuating value. Basically look at all the different measurements and divide them like you normally would, get the middle value, the average value, and then look at the range of values to get your uncertainty. Okay? So if we had a bunch of values like 2.0, 2.1, 2.2, 2.0, 2.1, 2.1, 2.2, 2.3, 2.1, right? Well, the average of that, average is 2.12222 repeating, so we'll call it 2.12. And then if we want to include all the values, we could say that the average with uncertainty is 2.12. The lowest value is 2.0. The highest value is 2.3. So if I'm going to include both of them, then I would need to have it say plus or minus 0.18. because that will make sure to include that highest value, and it's going to include the bottom value as well. So you come up with your uncertainty value based on the range of values that gave you the average. Only issue here is now we've got to round. Got to follow our original rounding rules, which is what I get to down below. Remember that you can only have one digit of uncertainty. So first off, I can't have 0.18. I should make that plus or minus 0.2. That, if anything, overestimates the uncertainty rather than underestimates it. And now if I've got my uncertainty in the tens place, I've got to round this off to the tens place as well so that they match. So the second rounding step is making my value 2.1 plus or minus 0.2. If you notice, what does this really mean in terms of my uncertainty range? It means that I think it's from 1.9 to 2.3, and that does include every value in my range. So this is a fairly accurate way to represent the average. Okay. The steps that I list down here below are just that, those rounding rules. Only have one digit of uncertainty, and make sure that your final value gets rounded off to match. Okay. And I know some people don't like rounding away values like 0.12. You know, the calculator gives it all those extra twos, and then it feels weird to round off to this 0.1. But remember, your final value, you should only be stating it as precisely as your uncertainty, as you know, the limitations of your equipment. And so once you have the uncertainty and you get it to one decimal place or one digit of uncertainty, that determines where you have to round off to. So keep that in mind and don't feel too beat up about it. Okay. So just as a couple of final reminders, when you're assessing results in experiments, the final absolute uncertainty of an experimental value gives a measure of how precisely it is known. There may be sources of random error that you didn't take into account in your uncertainty, but remember that range here is telling you, when you say 4.8 plus or minus 0.2, it's telling you that you know the value somewhere between 4.6 and 5. Okay, and you don't know it any more precisely than that. Even though you call it 4.8, you really only know it's somewhere between those two. Okay? The accuracy of experimental results are assessed by comparison to literature values and by calculating error, or usually percentage error. So you have to, in order to assess whether or not you're accurate, you have to compare back to what the expected or accepted value is, the literature value. When you are suggesting improvements for these types of errors, random errors, if you're going to make less random error, you can do a couple of things. You can either use more precise equipment, like a balance that reads to more decimal places. That's pretty much what you're limited to, or you can perform more trials, because performing more trials, eventually the pluses and the minuses of the random errors should cancel out, and you should get an average value that's closer to the real value. So more trials can be a suggestion for fixing random errors or improving them. Systematic errors can really only be improved by modifying your procedure. So that could mean, doing the procedure more correctly, reading the meniscus at eye level, adding insulation to your setup, or it can mean calibrating your equipment. But you can't perform extra trials, because since the errors are knocking you off in a direction every time, they won't be canceled out by additional trials.